Okay. So last class we left off at capacitance. I gave you a bit of a introduction to what capacitance is and what the definition is, types of capacitors and setup. One this. I mean, there could be multiple possible setups, but yeah, that is one. Then you have this possible setup where you have parallel plates working together. That is another possible setup. Now, what we're going to get into today is the entire working procedure of a capacitor, right? So we're going to look at how the circuit works when you have a capacitor introduced in such a circuit, right? So we're going to see how it gets charged up and how it gets discharged. We're going to work with energy, a bunch of different things, right? So, first thing, how do capacitors work? Take a look at the diagram you have in front of you. So that is this one. And I do have in details all the steps that is happening over here. And I'll walk you through those bit by bit. The first thing you want to look at is this portion. I'll change my marker. This portion that you see is in essence the capacitor, right? There are two parallel plates, one A and one B. When I say it's plate A, consider it to be the positively charged plate. When I say plate B, consider it to be the negatively charged plate. Fair? So I will keep referring back and forth between a positive and a negatively charged plate. Now, the second part of this circuit that you have is a voltmeter. Last class, I did give you a bit of a pointer. What it does, it measures the potential difference across any part of the circuit. So if you have the voltmeter attached over here, what does it measure? The potential difference of the cell itself. Fair. So if you have a cell with, 12 volt of power supply, and you have a voltmeter across this, what does this voltmeter measure? 12 volts. Very simple. So the same thing happens when it is put across a capacitor. Why would it take up the same voltage as the cell? We're going to discuss that. Okay. So now the other component I want you guys to be familiar with is the ammeter. Okay. What is the ammeter doing? It is measuring what amount of current flows through the circuit. Fair? So these are all things you're aware of in your AS, also in your GCSEs. So I'm just giving you a bit of a pointer. Now there's also something called a resistor over here in this circuit. The reason for this resistor to exist is to control the amount of current that I have in a circuit. If you remember this formula, V is equals to IR, if I increase or decrease the resistance, I control the current in the circuit. Okay, so the resistor becomes a very important independent variable in this entire circuit, where if I change the resistance in the circuit, I can control how much current flows through the circuit. Granted, I have a fixed supply of voltage. So let's say I have 12 volt supply of um, a source electricity, a power supply it can be, or it can be a battery. Anything it can be. So granted that power supply voltage is sort of fixed for me, how do I determine or select the current that flows through the circuit? And an easy way to do that is toggle with resistor. You will hear about thermistor, you'll hear about other variable resistors, multiple sorts, and fixed resistors as well that comes with a specific rating. For example, 5 ohm, 12 ohm, 15 ohm, whatever it may be. Okay, so those are the components you have in this circuit. The other component that you have is a switch, a typical switch. Now it is closed. The moment I open it, it looks something like that, right? So you break the circuit. That is how a switch operates. That's all of the things that I said is to refresh the key concepts in your mind. Okay. Now let's see one by one. Here, there's a capacitor setup, and there's an ammeter which will measure the current throughout the charge and discharge. process of the capacitor, and we'll get through how the charging process happens. So initially, when I have the cell over here, this is providing the electromotive force, or it is providing the voltage for the current or the electrons to flow. If I have 12 volt of voltage being applied, that means between these 2 points, I have a potential difference. I have what? A potential difference worth 12 volt. And I want to build this intuition inside you that whenever you have some sort of potential difference between any 2 points, current should flow. The point of applying this voltage is to allow electrons to flow. Okay, so often in your younger years, you have probably given this analogy that potential difference basically means, or it can be analogous to going from a higher step to a lower step. If you release a ball over here, it will fall down to over here. And that is a potential difference between 2 points. Sure, can think of it in this analogy, no problem. But in essence, that idea is right. And what you at the core need to understand, there is a difference in buildup of charge over here. That is denoted by the potential difference. The higher the voltage, the higher separation of charge that you have in terms of the potential they have. You just studied electric fields. You just studied electric fields. And over there, you know what potential really means, what electric potential really means. It means there is some amount of energy there stored. Okay. So what is really happening over here is the cell provides a source of energy, and that potential difference, that word potential difference really means somehow the charge is separated over here that causes electrons to flow. Okay. So if there is a large accumulation of positive charge here and large accumulation of negative charge here, the circuit is built in such a way that it allows the electrons to flow from here to here to here and come back to the positive side, such that such that it can nullify the net positive charge over here, make it neutral, and nullify the net negative charge over here and make it neutral. That is the point or the reason electrons want to flow. It wants to get to a state of neutralness, right? That is why we have the electricity flowing. That is why the EMF provided runs a circuit. Fair enough, we understand why the electricity starts to flow, or the electrons start to flow. That's great. Now, the cell provides the initial voltage. That's great, hence the energy provided. And what happens next? You have a resistor built in here. Why? So the resistor, what it really does is it slows down the electron flow by sharing some of the potential difference such that the capacitor does not burn. And this is why we have the resistor. I told you initially, towards the beginning of today's class, that what a resistor does is controls the current in a circuit. How so? V is equals to IR. And if you agree with me, if I control, granted this is fixed, the voltage is fixed. Granted this is fixed, if I vary the resistance, right, in the circuit, I can control how much current flows. If I increase the resistance, what happens? More obstruction for the electrons to flow, less current. And what is the definition of current? Rate of flow of electrons, in essence, right? So if I increase the resistance in the path, I'm decreasing the current. Fair? Hold that thought. Now, what happens? I could show you a demonstration over here, but I don't have the setup with me. But when you have no resistance in the circuit, granted the wire has zero resistance. Often we make this assumption when working in electricity. But granted the wires have zero resistance, right? And in that case, you know what will happen? Whatever voltage I apply, right, the setup will catch fire because the current running through the circuit will be so high that it is not possible to have a feasible circuit running. It will just catch fire because the current running through the circuit will be extremely high. And that is why we have a requirement of a resistor over here. Now, in real life, you necessarily need a resistor to control that or to make sure my setup doesn't catch a fire. Um, may not, depending on how good the wire is in conducting. So if the wire has some amount of internal resistance, so you probably worked with this idea already, internal resistance of certain materials back in AS probably. So if now this wire has its own resistance, right, then it means that it's all right. If the setup will not catch fire, there's already some amount of resistance and energy is being lost as current flows through every part of this circuit, right? Energy is lost throughout. And potential keeps dipping through every centimeter or inch or every millimeter that the current keeps flowing through the circuit because there's internal resistance in the wire. Fair. But granted, I have zero resistance in the wire. I need to have an external resistor for the sake of the argument so that I can control the current and my setup does not burn. That's the point of the resistor. Good. Now, the problem with this, though, technically speaking, is some of the voltage potential difference will be shared with the resistor. That is something that does happen. So as electricity does flow, as current does flow, some of the potential difference or some of the voltage is shared between this resistor. And if I supply, let's say 12 volt, technically speaking, that voltage across this will not be entirely 12 volt. It will be a bit less. But we're going to make an assumption over here that granted I'm supplying 12 volt of voltage, the potential difference across A and B, the capacitor, will also be 12 volt. Okay? Will also be 12 volt. That's just an assumption that I'm making, that we tend to make for the problems that you're going to be solving. Okay? Now, you may have set up where there's a resistor and the potential difference is quite shared between the capacitor and the resistor. That's fine. But let's assume that whatever potential difference I'm supplying, in essence, the PD across A and B will also be the same. What is the reason it could not be same? The main reason is some energy will be lost at the resistor over here. But anyways, let's move on with the idea. First thing, why do we need a resistor? It controls the current in the circuit. Next, let's move on. As we close the switch, right? As we close the switch over here, electrons start flowing. Where from? Like conventional current, sure, the arrows will be from this side to this side. So from the positive end of the cell to the negative cell. That's the conventional current route. That's fine. But let's say we're talking about the real current, the real flow of electrons, because electrons are the only particles that tend to flow positive charge. That is, the protons obviously don't flow. So the real current, in essence, I am talking about the electrons, and they're going to flow from the negative part to the positive part. Moving on with that idea, as the electrons flow from the negative part, from the right hand side, that is, left side, some PD will be shared with the resistor. That is to say, some energy will be lost as the electron passes through the resistor. And then what they will do is they will end up accumulating on plate B. What is plate B, guys? Plate B is the plate which becomes negatively charged. And do you know what this space is? It's simply air. No conduction is happening in this white shaded area. Okay? Keep that in mind. It is simply air or vacuum. No conduction is happening over here. It's not connected. Plate A and plate B is not connected. Keep that in mind. Okay? So what is happening now is as the electrons keep moving, the current keeps flowing, right? The current keeps flowing and the electrons are accumulating on plate B over here. And there is suddenly a great accumulation of negative charge on my plate B. And what is the problem of that? Not a problem, but what is the result of that? What is the consequence of that? As you have a greater accumulation or storage of negative charge over here, it will repel all the negative charges, that is, all the electrons on plate A, and a lot of them, if not all, right? Why? Because like charges repel. That's the basic idea over here. So as I s- provide some amount of electron flow using my cell, what it does is it gets stored on plate B, accumulates over here, stores the negative charge, and in result, it induces a positive charge over here. Mark my words over here. It induces a positive charge. Very important statement. It doesn't conduct through this space. What it does is it induces a positive charge. How so? As the negative charges keep accumulating over here, it will result in the negative charges over here being repelled. Okay. So as a byproduct of this process, positive charges build up because they can't move. And why will they move? They're attracted to the negative charge. Fair? So what do these electrons do? What do these electrons do? So they are basically now flowing to the other side. So typically, if you had this part connected, what would happen? Electrons would keep flowing and complete the circuit. But we have a blank space over here. There's air over here. So the intuition of a typical, working with a circuit is this circuit is not complete. There's air over here. How does this work? How it works is via induction of positive charge over here, causing negative electrons to move around in this direction. And at the end of the day, you do indeed complete the circuit. So electrons flow, right? And they complete the circuit by arriving at the positive part of the battery or the whatever supply of electricity you have. So this is how, even with a capacitor, which has air in between or space in between, blank space in between, a circuit can be complete. This is the working of a circuit. Okay? With capacitor, that is. So that is pretty much what I have shared over here. Okay. And this process of accumulation of charge, by the way, continues until this potential difference is equal to this supplied potential difference. And this is where I may ask you guys to make the assumption that for the sake of this diagram, for the sake of this setup, just assume that whatever potential difference I'm supplying, that is the exact potential difference provided to this capacitor as well. Forget about the resistor over here. Okay, resistor is needed and in setup for good reason, and I explained why. But for now, just know that the sharing of the voltage is negligible, and ultimately, the PD that you will get using a voltmeter will be around 12 volt as well. Okay, so whatever supply of voltage I'm giving, it is carrying the same potential difference as the supply. So basically, again, if I have to package whatever I said in a different way, what would I say? It's simply this, that when I have a cell being provided, right, whenever I have a supply of electricity being provided or battery, the electrons keep accumulating over here until the charge build up over here equals the charge build up over here, and the charge build up over here equals the charge build up on this part of the cell. So basically what it's doing is it is creating the same potential difference as the supplied potential difference. Okay, that is exactly what's happening. So the current keeps flowing until the plates over here are somewhat equal. Okay, and that is when this completes, right? When you have the same potential difference across these 2 points and these 2 points is when the capacitor is done being charged up. Beyond this point, the capacitor doesn't no longer get charged. It does no longer store further energy. The circuit keeps moving. That is to say, the electricity keeps flowing. I'm not going to say that the electricity doesn't flow. Obviously, it does, because there is PD across these 2 points causing electrons to flow. It is simply that charge will no longer build up over here. Charge will no longer build up over here. The build of charge gets completed the moment this is 12 volt and this is also 12 volt. The supply voltage doesn't change. It's just that the potential difference over here keeps increasing until 12 volt is achieved. That is the core key idea. Okay. Any question till this point about how the capacitor is getting charged and what the process is? Any question till this point? Yeah. No. Okay. So hopefully we have the normal understanding of how capacitor gets charged up. Fair. Good. Thank you. Now we'll move into a few different things. Yeah, obviously, electrons don't flow through the air gap. Two formulas I want you guys to remember, flashback, is one is I is equals to Q by T. That is rate of flow of charge, how much charge is transferring every second through the circuit, through the wires. The other is voltage can be explained as work done per unit charge. What does this resonate with? If you ask me, electric fields. Do not let go of one topic when studying another topic. A lot of the topics in A levels are interconnected, and usually when it's taught to you, it will be taught in an order. I mean, the syllabus is designed in an order where one of the topic helps understanding the next topic. Okay, and the key ideas are explained in the previous one, so that you can move on with certain explanation with the next topic. So remember electric potential in the last topic, electric fields. When we were having that discussion, what did we say? When we're talking about electric potential, we say it's the work done per unit charge in bringing it from infinity to a defined point. So that statement, that work done per unit charge, in essence defines voltage as well. So that is why when you have the previous diagram, if I show you to you guys, I mean, I did explain once over there, but that is why when you see these potential concentric circles or graphs, it is denoted as voltage. Okay, 5 volt, 10 volt, 20 volt. When you have this again, 20 volt, 15 volt, 10 volt. Why? Because the definition is pretty much the same, work done per unit charge. So the key idea is the same across. Anyways, coming back over here, two formulas. Current is equal to charge per unit time, and voltage is work done per unit charge. We'll be using these two. Let's see now a few graphs. And I'm telling you guys, these three graphs are important for you guys. You need to understand these three graphs. May come and most likely will come if this topic does come. Okay, one is how the charge varies at the capacitor with respect to time. And when we are drafting this graph, when we're drawing this graph, this charge denotes the charge on one of the plate. Keep that in mind. On what? One of the plate. Because if I recall for you guys, what did I say is the definition of a capacitance? The charge stored per unit potential difference on one of the plate. Why is that? So again, a bit of a repeat is granted I'm providing the same 1 volt of voltage of potential difference applied. That means with this 1 volt, how much charge can my capacitor that I'm testing can hold on one of the plate? How much charge can this capacitor hold in one of the plate? The more charge it holds, the more energy it can hold with the same voltage. So let's say one of the capacitor, whatever the capacitor may be, stores 20 coulomb of charge, let's say negative charge on this plate, and 20 coulomb of positive charge on this plate. Just because on one plate I have 20 coulomb of negative charge and 20 coulomb of positive charge, does it mean net they have stored 40 coulomb of charge? No. It doesn't matter if on one side I have negative 20 coulomb of charge and the other I have positive 20 coulomb of charge. The point is, at the end of the day, if I transfer, if I induce 1 coulomb of positive charge over here, that automatically means I have net 1 coulomb of negative charge on this plate, which resulted in a net positive 1 coulomb of charge on this plate. So you don't have to say that I've stored 2 coulombs of charge on my at my capacitor. When you say there's 1 coulomb of negative charge on one plate, that automatically explains that on the other plate, obviously there's a positive charge worth 1 coulomb. Okay, that is why we say the charge stored per unit voltage on one of the plate. What would happen if I stored 20 coulomb? I have stored more energy. What is voltage? Work done per unit charge, right? So what would the net work done be? Voltage times charge. If I increase the amount of charge, I'm increasing the amount of work done or the energy stored. Get the idea? Yeah. So that is why the capacitance metric is important, right? And that is why we define it as such. So when you have this graph, what information is being provided to you? How much charge I'm storing on one of the plate. Okay, fair. So this we're going to see the graphs of charge, current, voltage with time in a circuit with capacitor. Okay, let's see. Give me a moment. So let's explain what each of these graphs mean. What is this? Yeah, I'll be explaining what each of these. What? Yeah, I'll explain what each of these graphs are. So first off, we have the charge graph. What is it showing you? Initially, the charge is 0. That's the first thing. Buildup of charge is 0. And as time proceeds, the charge buildup, the rate of charge buildup decreases. And the total charge buildup plateaus to a value Q naught. That is the maximum amount of charge that can be separated by the capacitor. Fair? But what does this gradient mean? What is the gradient of this curve? Del Q by del T. That is what it, in essence, the gradient is. Del Y by del X, right? That is how we define gradient. Fair? So if I have del Q by del T, what does this mean? Amount of charge stored per unit preceding time. With every change in seconds, how much charge am I storing with the consecutive change in second? Simply explained, as time proceeds per unit time, how much energy, how much charge am I storing? Fair? So why is it that the rate of charge flow or rate of charge stored initially is so high? I'll explain it to you. Because initially, B is charged as what? Before I charge up the circuit, give me in the chat or unmute and tell me what is the charge on plate B before the circuit starts, before I close the switch. What is the net charge on plate B? Tell me. Anyone? Yeah.
It has no charge.
It has no charge. Perfect. So it has zero charge. It is neutral initially. Same with plate A. Nothing has happened. Current doesn't flow, right? It is not a closed circuit. So initially it has no charge as a capacitor, right? And that means something interesting. If this has zero charge, however, over here there's a net negative charge that is on the negative side of the supplied EMF, right? What that means is there's a certain potential difference or between these 2 points, which allows the electrons to flow very fast to this over here. That is plate B. Because there's a high concentration of electron over here or negative charge over here compared to over there on plate B, which is zero charge, net zero charge. So what happens? Electrons start flowing really fast. But 2 seconds later, what has happened now? Some electrons are now stored on this plate. A few, but they are stored on this plate. So what happens now? Now the electrons see, damn, I have some electrons on the other side. They're repelling me. I will proceed very slowly. So what has happened now? There's some amount of repulsion from this plate B to the incoming electrons. There's what? Some amount of repulsion from plate B to incoming electrons. What does that result in? That results in a slower build up of electrons or charge on plate B. So initially, the rate at which the charge was coming or the electrons were coming, very fast. As time proceeds, what happens? Rate at which electrons come in decreases. Okay? Electrons are still coming. Charge is still building up. Charge over here is not becoming less. It is still decreasing. That is, the negative charge is increasing, but it is happening at a slower rate. That is what I want to put in your head. That is why I said the gradient is decreasing. And what happens when the capacitor is fully charged? No more charge is built up. So it plateaus down over here. Get the idea? That is why it plateaus down over here. No more charge is built up. Well, the potential difference across this and across this is equal. That's the key idea. Okay, that's the key idea. So when the capacitor starts getting filled, the rate of charge flow decreases since less place left for the electron to deposit, and there is repulsion from the plate B. Okay, that's the key idea. Any question so far? If so, ask me. Next one I'll move, and the next one is current. Okay. Now, it is a bit intuitive over here, as you have already seen. Already seen this one. It should be a bit easy to understand why current is shaped like this. Somewhat opposite, not opposite, but related to the gradient of my initial curve. Let's see how. So initially, the current is max. I naught over here. And as time proceeds, current decreases eventually to zero when everything is charged up. Okay, the capacitor is charged up. The circuit is still complete, but the current will eventually fall to somewhat zero. It is not exactly zero over here, but it will fall to somewhat zero. It doesn't exactly meet over here, but it will decrease to a certain value. Okay, the circuit will still be complete. There will still be some potential difference shared between resistor and the capacitor. No problem with that. And if there was a bulb over here, the bulb would still light. It is simply that the rate of flow of electrons will eventually decrease to somewhat zero. Why is that happening? Let's see the initial curve. What is this telling you? The gradient del Q by del T. Okay. So change of my inflow of charge divided by the time it took to come there. Okay. So initially, as you see, it is very steep. So a lot of charge is coming per unit time. As time proceeds, the number of charge coming in per unit time decreases and plateaus down to zero. Okay. The flow of electrons, rate of flow of electrons decrease. Okay. That is the key idea over here. So analogous to that, I have my graph over here. Initially, it's max current because a lot of electrons are flowing, and eventually, as you proceed and plot, the current drops down to zero. Again, circuit is still complete. Okay, circuit is still complete. It is not that I've opened the circuit or anything. It is simply that the charge buildup is complete for the capacitor. That is it. So, as mentioned over here, I is del Q by del T. Since I is the amount of charge traveled in a period of time, the gradient of the QT graph gives the value to be pointed in the IT graph, that is current versus time graph. So when my gradient is zero, the current value is also zero. Fair? So these two are what? Interconnected. We get that idea. And such questions can come your way. Just saying. Next, what do we have? Last one that I'll talk about is voltage versus time. Okay. Voltage versus time of what? The potential difference being created at the capacitor versus time. Fair? Now, initially, what happens? Initially, do you have a potential difference across the capacitor? No, right? As you mentioned, the charge over here is zero, the charge over here is zero. Should there be any potential difference between these 2 points? Not at all. Not at all. So initially, my V value is what? Zero. Okay. And as time proceeds, the potential difference increases across my capacitor. And doesn't this look oddly familiar to my first curve? Of course it does. And for good reason. Because the voltage that is being applied across the capacitor or the voltage buildup at the capacitor depends exactly and proportionally to the charge buildup. Why would there be a voltage buildup if there is no buildup of charge? Simple, right? So as the amount of charge deposit increases on either side, that is, if electrons deposit over here a lot, in return, a lot of positive charge gets induced over here. And as this increases, as this charge deposit increases, with time, the potential difference also increases between these 2 points. Okay. So this and this is exactly proportional, hence the same shape. So basically what we have is, you know about this relationship. The voltage is exactly equal to work done per unit charge. Okay. So what do we see over here? That I mean, for one thing, as the number of charge over here increases, right? Um, the rate of flow of the charge that you have will decrease with respect to time. So initially you have a really high flow of electron, and later on you have a less flow of electron. Okay, so as initially you have a lot of electrons coming in, so initially you have a high rate of voltage being built up. So initially when it's going from 0 to 1 volt, it is happening rapidly, really fast within a short span of time. The same increase from 1 volt to 2 volt is taking a lot more time. It's still an increase of 1 volt, but it's taking more time. Why? Because number of electrons coming in has decreased per unit time. Okay, so that is why you have the similar shape again, if I had to explain. Fair. So that is why you have the voltage curve with respect to time being analogous to your typical QT curve. Okay. So all of these three things you can take a screenshot and try to think of it. If you have any question, do ask me right now. Charge is okay. Okay. Any question till now so far with things I have explained? Graphs are all good. Fairly simple so far. Okay. Okay. Great. Now move on to the next thing. So I explained last class that why the energy is stored in a capacitor, and I tried bringing in the idea of electric fields, which is exactly what it's analogous to, what it's similar to. Like I've explained the battery example, then okay, okay. So I showed you guys last class what happens when you have a typical cell, and when the charges are mixed up, what happens? There is no net potential difference across this point and across this point, right? So ultimately, they have mixed equally in between themselves, the charges, I mean, and hence there's no potential difference. Now, if I want to separate the charge, that is, granted my positive and negative charge want to be attracted to each other, right? And it's equally distributed, the charges. Now, when I come in an external factor, an external force, what happens? I start separating the charges. Oops. I start separating the charges such that I have a bunch of positive charge build up over there and I have a bunch of negative charge build up over here. What did I do? I did work done to separate the charge. Do we relate this to electric potential energy or gravitational potential energy from those two topics? We should. When there are attractive forces and we separate them, pull them apart, we are doing work on them, right? We're providing our energy to them. So they go from a more negative EPE or GPE to a less negative GPE or EPE, electric potential energy or gravitational potential energy. So we're providing our energy to do that. So the same thing over here in a cell, when you're separating the charges, again, we talked about class how this is the exact same thing that happens in cell phones, right? And other cells. So the same thing over here, when you're separating charges, you're storing energy over here, basically, right? You're storing energy over here. And with time, what happens is as you demand energy, basically the electrons will start mixing up with the positive charges, and that flow of electron, that it goes from a negative charge placed to a positive charge placed, or it's basically decreasing the potential difference. That flow of electron is allowing you to use your phone, use your tab, use your computer. It is this flow of electron over here that is allowing the charge of your device to decrease. Okay. So when I separated the charges over here, I stored some amount of energy. And now as I start using my device and I demand energy, this basically will be, there will be a flow of electron over here. And as it proceeds, the PD over here decreases and the stored energy goes to zero. Because after a point, there will no longer be a separation of charge. And what will happen is I need to charge my device up again by some amount of external force. And what is that external force, or what is, who's doing the work done? We take energy or power or whatever you want to say, the supply from our main wall, or the main grid supply of electricity, or you have a battery, who knows. So that is how we externally charge up our devices. That's how the entire process works. Now, in essence, what do we use capacitors for? I understand it stores energy, I understand how it works. So till now, what are we clear on? We know how it looks like, right? Then we know how it works in a circuit, and we know it stores energy. There are a few things we're clear on. These three are the things so far. And when the question in your paper asks you, what are the uses of a capacitor? There are three things that you just say without any hesitation, and these are the listed three things. It may ask you in the past papers. There are these questions. Some of these you won't understand now, and that is completely fine. For the topics need to be explained to you for you to understand that. First is it stores energy. You're 100% clear on this. Second is it blocks DC signal. Well, mm, for now, just understand this. We need to go through the electricity chapter for me to explain this. And the other is it is used in sensors. These are three things which you should know about the use of capacitors. The other is smoothens AC. And this one you'll see very extensively in the alternating current chapter, how the smoothing happens. I'll show this to you. So basically, there's three, four things you need to know when asked the question, what are the uses of capacitors? So stores energy, blocks DC signal, DC direct current, basically. So there's it's unlike alternating current, it is simply one flow of electron, electricity. So it's a direct current. Now, the third is it's used in sensors, and the fourth is it smoothens alternating current. Okay, fair. Now, the formula of capacitance. I mean, intuitively, if by definition you have to write it, you should be able to. What do we know about capacitance? What is the definition of capacitance? Charge stored on one side of the plate when 1V supplied. Fair, in short, in a succinct manner, this is the definition of a capacitor. So if I had to turn this into a formula, what would I write it as? My capacitance value of a capacitor is given by charge on one plate divided by per unit voltage. Okay, per unit voltage. So this is how I would write the formula. What this will give me, so if I plug in 10 volts of supplied voltage in a circuit, and the charge stored becomes, let's say, 100 coulombs. Okay, what will my end result be? It will give me capacitance as 10 coulomb of charge is stored per unit voltage, and we call that value or unit, sorry, unit farads. 10 farads will be the capacitance of the capacitor, which tells me, so 10 farads tells me that for this capacitor that I'm working with, this capacitor will store 10 coulomb of negative of or positive charge on one of its plate when 1 volt of potential difference is applied. Get it? And that we in short say as farad. What is this? So that in short we say as farad, 1 farad. Sorry, 10 farad. Now, another thing is when you're working with farad, usually you'll be working with microfarad. So you will be used to this symbol, micro, micro farad. Okay. This you will see very often. Why is this? Because of often the capacitance rating is in micro. Okay. It is in micro because the capacitance value tends to be very small. So if capacitance value tends to be small, what is it that is actually small? The charge stored tends to be actually small. So the amount of charge stored in a plate tends to be really small or in the micro values. That is why you have microfarad usually. And the other thing is, I want to tell you guys something. Okay, that is the next thing. I again show you the three functions of capacitor. So you can write these or take note from this as well. Okay, the one thing I did want to explain to you guys is a few factors affect the capacitance. So I'll draw a capacitor for you. Okay, typical capacitor. This is a plate. This is a plate, and this is okay. So power supplied. There's a power supplied, and there's a capacitor here. There's air in between, and what is happening? Whatever power I'm supplying or the voltage I'm supplying, that is being applied across these two plates of the capacitor, and the PD across these two will be, oops, 12 volt as well. Fair. So it will be 12 volt over here as well. That is as time proceeds. Now, the amount of charge stored over here, or the capacitance rating. Okay, that is what I want to talk about. The charge stored on one of the plate is basically what we are worried about when we talk about capacitance. It can increase or decrease. If charge stored increases, that means more energy. More energy stored. Okay. Now look, what factors affect the capacitance? One is area of the plate that you're working with, that is the size of this plate, how wide and tall the plate is. So if I look from this side, how big is my plate? How tall is it and how wide is it? Okay. So the bigger the area, the more charge it can store. That seems quite intuitive, easy to understand. If I have more space, I can accommodate more electrons. Fair? So if I have a capacitor which is shaped as or built as a bigger device, or it's bigger in size, that means I intuitively know that this capacitor, granted I'm comparing with another capacitor of the same material and smaller size, then the bigger one will have more charge stored on one of the plate, hence a higher capacitance rating. Fair? So as my area increases, by the way, material can also affect. But anyways, as my area increases of the plate, okay, the charge stored on one of the plate will increase. So the other thing is the plate separation. I kept telling you guys that there is air in between, and I told you that typically when you have space in between, uh, In a complete circuit, that means the circuit is not complete. But in this case, since induction is taking place, that means the current will flow. Now, the point is, this air must affect somewhat, right? This air over here must be causing some nuisance. I understand it induces and completes the circuit, but isn't it worse off than just having a connected wire? Obviously, it is in terms of the current flowing. But in essence, I can also toggle with this area that I have, or the space in between that I have, to decrease or increase the capacitance of the capacitor. What do I mean by that? So basically, if I have a wide capacitor as compared to a very narrow capacitor, when electrons are stored on this plate, it will have a harder time inducing a positive charge over here because they're further apart. They're what? Further apart. What do we know about electric fields? As you move away from charge, the strength of that force or electric force decreases as you move away from it. The electric fields. What happens as you move away from the charge? The field strength decreases, right? The force that can be applied decreases. Same thing over here. So as you move away from the charge, what's happening? It is harder to induce. So the charge build up on either of the plate will simply decrease. Will simply what? Decrease. So the capacitance with a large separation is less, while the capacitance with a small separation is larger. So plate separation is inversely proportional to the charge stored. More separation, less charge. Or if I want more charge, plate separation should be less, whichever seems intuitive for you to understand. Now, type of material between the plates, air, vacuum, that affects. So basically, it is more of a conversation of the permittivity of the space, which you guys don't need to get more into. You don't need to understand that much. But basically, the space that I have in between is this air? Is it vacuum? Is it solid? Is it liquid? Do I have this set up inside water? Is it distilled water for some reason? Where do I have this? What is the space that I have between the capacitor plates? That dictates how well a positive charge can be induced over here because it affects the field forces of the charge. Okay, so basically, when you have a space in between, that affects how the charges interact with each other. Okay, so when I have typically when you have a vacuum, it's better induction and whatnot, and we stick with a permittivity value. I don't think you need to work with this, but basically saying you do need to work with this actually later on. I'll show it to you. But the value that we work with, why does this keep happening? Yeah, so the value that we will be working with for the permittivity of space inside will be that of a vacuum, and that is considered as E naught. Fair. So you can dive more into this if you wish to online. If you want to learn a bit more on the side, no problem. I'll be happy. But basically, we consider one value for permittivity, and that is a vacuum. In essence, three things, three factors. One, two, three. One is area of the plate that you have that affects the capacitance. Two, the plate separation, how far they are from each other, that affects the capacitance. Third, what kind of space you have in between the plate that affects the capacitance of the capacitor. Okay. Third thing is this is from your paper, from one of the past paper, that there are three functions of a capacitor in an electric circuit that they asked, and you could say one is smoothing, as I said. I'll show you how it looks like later on when I teach you alternating current. The other is it provides temporary power supply. So if it has some amount of energy stored and there's a PD across it, goodness. So if there's a potential difference across the two plates, for some time as it discharges, it will provide the energy to the appliances in the circuit. So what do I mean by that? So if there's a bulb over here, right? There's a bulb over here, and it lights up when you have a complete circuit, and you turn off the switch. Sure, you're cutting it off from this supply of energy, or you just completely shut off the energy supply. If granted you have uh, it's some sort of appliance connected to this capacitor, then for some time after you cut off the power supply, main power supply, even then for a few seconds the bulb will light up. So for some time you will have energy being supplied to the bulb. Okay, so what's happening? For a few seconds or minutes, however, whatever the type of capacitor you have, it will be discharging energy such that the appliance in the circuit gets that energy. And if I'm talking about a bulb, it will light up for a few more seconds. Some people I have heard give this example, maybe true, I don't know, in your fan, when you do have, it, I don't know, you turn off the fan or the power supply goes off for a few seconds. There's inertia as well. Obviously, it will have inertia and it will turn around for a few seconds, but I don't know. There's probably a capacitor. Some people have said this. I'm just repeating that. And for a few seconds, the fan will go on moving around because there's a capacitor in the circuit and it is discharging energy. Okay, that is true. So that is pretty much how you see capacitors being used. Okay, that is pretty much how you see capacitors being used. So what happens with the capacitor is that energy, that potential difference, it decreases with time. So it discharges, right? The energy discharges. Whatever stored energy there is, it decreases with time. So basically, whatever appliance is working, it comes to a slow stop. Fair? So now there's smoothing, there's temporary power supply, there's surge protection. What does this mean? Basically, when there is a sudden insurge of a current flow, what happens? It stops from it being directly conducted, or it acts as a barrier. Because the point is, you need to charge up the capacitor such that your circuit is complete. What do I mean by that? You need to charge up this plate such that it induces a charge on this plate such that the circuit is complete. If there's a sudden surge of electricity, it won't work. It won't really affect you because current won't directly flow through the wire and just ruin the circuit. No, it won't. Why? Because space in between. Induction takes place. You're inducing charge. So it's we can say it's surge protection as well. I mean, in typical electrical setup would be way more complicated than I'm showing over here. I'm oversimplifying it. You will have parallel setup of capacitors. You will have series setup of capacitors, and you will see. I will explain those as well. So when you're doing problems, it will be a more complicated setup, which I'll show. Don't worry. And the fourth thing is time delay. This you will learn in alternating current. Okay. So a few things. These are the three things you can talk about. Four things you can talk about when talking about uses of capacitors. Let's see what I have. Okay, yeah, it is an alternating current. So when you do study alternating current, you'll see it. Uh, Time delay, smoothing effect, these are things you'll study. Next thing, we'll talk about deriving formula of spherical conductors. Sure, capacitors. This is what I'm talking about, how capacitors act when they are put in series and how they're put in parallel circuits. So in parallel, they basically, uh, as you can see, add up. And in series, they follow this odd rule that we follow for resistance in parallel. So I'll show this to you, and that is going to be very important when solving circuits with capacitors. Okay, that's one of the more important chapters, which I'll come to now. How does capacitance for isolated sphere conductors work? A bit of a niche topic, but I'll explain. So what do I have? I have a bit of a conducting sphere. What does a conducting sphere mean? It conducts electricity. That's it. So you have a charged sphere. It is positively charged, and it is connected to a power supply. Okay. So what this is basically some sort of a cell. Okay, let's consider this some sort of cell, some sort of main supply, which is providing the potential difference for the current to flow. And this part is earthed. Okay. Okay. So now that is the complete setup. So we have positive charge induced in the sphere over here, and there. Why does this basically the point is why do we have a positive charge sphere? How do we make it happen? Basically, you can think of it very simply. When I provide this EMF over here, right, I'm causing all the electrons from here to travel to my positive part of the circuit or positive part of the cell. So that is how I am pulling in all the electrons from the sphere, and the rest of the electrons get to Earth. And that is why we have earthing, right? So, in essence, that is how you can make this sphere positively charged. Okay. So, basically, that is what I explain over here how you're getting that positively charged sphere. Fair. Um, until positive charge in the sphere equal the positive charge of the source, electron will flow. So, when you have this charge net, it will equal your supplied positive charge over here. The electrons will stop flowing. And at that point, you know that you have the same positive charge that will be at the surface of this conducting sphere. And one more thing that I will add over here, when you have a conducting sphere, all of the charge distributes itself furthest apart from each other or occupy the surface of the conducting sphere. So all of these, if they're accumulated over here, it doesn't matter. They will push out to the surface and occupy the space furthest from each other. Because that's where they get stuck, in essence. So that is how the charge is distributed on a sphere on the surface. So fair. Now, as this process takes place, you know that you are eventually charging the capacitor. Basically, this you can consider to be a capacitor. Is basically what the conversation is, because you're building a charge on the surface, and then there's some amount of a potential difference with respect to the center of the sphere. Okay, so there is some amount of a charge difference between two portions of the sphere, inside and outside. Consider this. Okay, that is the point. Okay, so I'm just extrapolating this idea and giving you guys how the charging takes place and how the capacitor really works. So what did I do? I provided some amount of a potential difference, a battery, main power supply, connected the positive end, connected the negative end, which was earthed, and then the positive supply causes electrons from the neutral sphere initially to flow over here. And what do I ultimately have? A positive charged sphere. And there's some amount of a difference in charge accumulation compared to the center and compared to the surface. So now, how can we measure what charge I am accumulating over here with respect to the voltage being supplied? So what this graph gives you is, as I supply a certain voltage over here between these 2 points, this is my supplied voltage, right? as I increase that voltage with respect to time. So over here you have the voltage axis, over here you have the charge axis. That is charge accumulation on the plate, on the conducting sphere. So as I increase the amount of potential difference applied, voltage supplied, how does the charge accumulated on the sphere vary? That is what I want to find out. Okay. And you guys know for a fact that voltage, if increased, the charge accumulation will increase in exact proportion. And can you relate to which topic I am connecting this with? Like we learned it today. And if you set the graphs over here, then you're right. Notice how the voltage and the charge curve is exactly same. It's in proportion. So as I increase the voltage supplied, the charge accumulated also increases, right? So both of these, charge and voltage, are in proportion. Fair? So sure, this is showing you the voltage, how the voltage is increasing at the capacitor with respect to time, and this is showing how the charge gets accumulated at the capacitor with respect to time. But the point I'm trying to make over here is, let's say the supplied voltage increases from 12 volt to 13 volt to 14 volt. What would happen in the capacitor? Wouldn't more charge be stored? Yes, definitely, and in exact proportion. Okay, in exact proportion, because C is equals to Q by V, right? And as you take this to the other side, as charge accumulation increases, voltage across increases as well. Or I can say, if the voltage supplied increases, the charge that will be accumulated increases as well. Fair? So that is the key point, that as I increase the voltage supplied, the charge stored at the sphere increases. And how are we storing this energy? Sorry, how are we storing this charge? I mean, yeah, storing energy as well in turn. But how are we storing this charge? We provide a potential difference. We cause a potential difference between these 2 points, and electrons flow, because this is initially neutral and this is initially positively charged. So electrons flow from here to here. Fair? That is how it's working. And as you increase the voltage supplied, charge accumulation increases. Now, where the real conversation is how do I find out the capacitance over here? I want to find out how the capacitance varies, or how I can identify the capacitance for this specific sphere, right? And typically, I know the formula to be Q by V. So it is fair enough of an argument to say, well, I can just not multiply, divide the charge stored over here with whatever voltage I supplied it with. Okay. So if I supply 12 volt and the charge accumulated is, let's say, uh, 10 microcoulomb in the sphere, then I just divide 10 by 10 and whatever the value is. So 1 microfarad, I guess. That should be my answer, right? Fair. That is not wrong. But what we're going to be working with is a different formula. We're going to try and find out a different way to decipher or understand what the capacitance of any conducting sphere is. Granted, I only know the radius and permittivity of that sphere. Let's take a moment to understand this. What did I say? So granted, I have a spherical conducting sphere, and there's a bunch of charge. This is a solid, or it's let's say it's not a solid, right? Uh, what I mean by it's not a solid is it's not filled inside. It is space. It has space inside, so it's empty inside. Okay. So granted that's the case, because in that case I can use permittivity as that of vacuum. I just explained how how permittivity works in the last subtopic, right? So for this equation to work, one thing I need to clarify for you guys, which I initially didn't do, is the space inside needs to be vacuum for the formula to work. Okay. So in that case, it works. So the space inside will be basically a vacuum because then we can take the permittivity of vacuum into the formula. I will show you guys how the formula is derived, no problem. That is the purpose of this subchapter. But we are considering this as a shell, let's say, of a conducting sphere. Now we get to a point where, granted, I know the permittivity of space inside and the radius of my sphere, I should be able to find out what the capacitance of this sphere is. That is what I want to find out. Okay. That is ultimately what I want to find out. Okay. Because I don't want to know what voltage value is, what charge accumulation is. I directly want to know what the capacitance is. So how do we do that? We do a bit of derivation over here, of course. So one of the formulas we are familiar with is Q is equals to CV. C is equals to Q by V. This you know, okay? The other formula that I want you guys to be familiar with or remember, recall, is this one. V is equals to KQ1 by radius. What is this radius? One by one, I'll explain the variables. What is this radius? Okay, that white marked space. So from the center to the surface of the sphere, what is the distance? That's the radius of the sphere. And charge, it's basically the charge on the sphere. By the way, both are the same. Charge on the sphere. Q1 defines charge on the sphere in both cases. What is the V value? K is the constant. So 1 by 4 pi epsilon naught. So 1 by 4 pi epsilon naught. That is the value of K. Anyways, so what is the value of, sorry, what is this electric potential over here? That defines if I have a certain, you learned about spherical conductors. So if I have a certain spherical conductor over here and it has a certain charge, as you move away from this sphere with respect to the center, how does the electric potential vary at every position? Where did you guys learn about this? Again, the previous chapter. That is why I said previous chapter is very important for learning this. So what is this? What does this give you again? The EP at every one of these positions. So for a spherical conductor, as you move away from the center, the electric potential will decrease. Let's say I'm bringing a test positive charge, 1 coulomb of charge, and this is a positively charged spherical conductor, right? So I do some amount of work done in bringing it from there, that is infinity, to over here. And as I move it closer, more work done. Move it closer, more work done. Move it closer, more work done. So every one of this position has a certain electric potential amount of work done in bringing 1 coulomb of charge from infinity to this point. Fair? So that those points define a certain voltage. Certain what? Certain voltage at each of those points. Okay. So that idea I'm going to work with. That voltage is what this V defines. Previously, you will have written this as EP. As what? EP. Do you remember? Electric potential? You should. So what did we have? EP over there. And it means the same thing. Again, today I gave you a bit of a recall when I was showing you guys the concentric circles, the potential concentric circles for a point charge or a spherical charge. I showed it to you guys. So going from 20 volt, 15 volt, 10 volt, how do the circles vary in the previous PDF that I showed? So that defines work done per unit charge, right? It's the same thing. It can be classified as the voltage, no problem. So basically, we have two formulas respecting voltage. Okay. One where this is basically defining the supplied voltage, not necessarily the supplied voltage, but it's going to be the same. Whatever the supplied voltage is, the potential difference accumulated in this charge will also be the same. Okay. Basically in this sphere. Great. Again, I'll repeat. So in case you didn't catch, the potential difference over here will be the same as what? The potential difference built in this sphere. Okay. So the shell to whatever this point, center point is. Got it? Keep that in mind in case you didn't catch that. Okay. So if I provide 12 volt, there is 12-volt potential difference in this sphere from center to surface. Okay. So call it supplied voltage or the voltage in the capacitor, whatever you want to say. No problem. Same thing. So now this is also the same thing in essence. How? If I put in the radius as radius of the sphere, is it not the same thing? It is. So what is the electric potential over here? Work done per unit charge over here at this position, surface. This equation is giving you the potential difference with respect to surface and the center. And this equation, if you plug in R as the radius, is also giving you the same thing because it is giving you the electric potential at the surface, which is going to give you the same value as this. Fair? That should make sense in somewhat manner. Okay. So that is why we are working with these two formulas. That is why working with these two formulas makes sense. Okay. Now, what do I do? I want to make the same thing the subject. Basically, I want to make charge the subject. I have charge common across both places, and it's a constant. What is Q1? It's a constant. It doesn't change. It is not a variable. Whatever charge I have built up, I have built up. Same value across two formulas. So I put both those as equal. So Q1 is equal to Q1. So CV is equals to whatever formula, AQ1 by R. My bad. So if you're VR by K, sorry, VR by K. So CV is equals to VR by K. And what did I tell you guys about the significance of V on either side? They mean the same thing. With respect to the fact that this radius will only consider, sorry, this R will only consider the radius of the sphere. So granted, my R means radius of the sphere and not any other position, no other position, only the radius of the sphere. In that case, the V value will be same across both the formulas. So I can cancel them off. There is no problem doing it. Once I've done that, what am I left with? Capacitance value is equals to R by K. Okay. And what did I tell you guys about K? It is 1 by 4 pi epsilon naught. Okay. So K is this. So if I put in C is equals to R by 1 by 4 pi epsilon naught. So it will basically reverse and reciprocal. So R is equals, sorry, C is equals to R times 4 pi epsilon naught. Okay. This is the equation that you get. Get it? So this is the expression or formula for capacitance of a spherical conductor, an isolated conducting sphere. Better phrased. Do we get this formula? This derivation, though, I don't know if it will come, but just it's easy. It's fairly easy. Just understand this. It's not too difficult of a derivation. I've showed probably harder derivation till now. You're just basically putting two formulas as equal. Hopefully, no problem till this point. So again, I want to make sure you understand what the formula at least means. So this formula means when you have a isolated conducting sphere, in that case, how do I find out the capacitance of that sphere? How do I find out? I just need its radius, that is distance from the center to surface, and the permittivity, permittivity of the space inside, which we consider to be E naught or that of a vacuum times 4 pi. And this and only this will give you the capacitance value of that sphere. Any problem to this point? Hopefully not. Okay. If you do, let me know. And classroom is always open in GC, so you can ask me there. Another thing, it's not wrong for you guys to use the C is equals to Q by V formula. That is absolutely not wrong. That is to say, if you know in a capacitor, right? Granted, this is a spherical conductor, conducting sphere, and it holds a certain amount of charge. Let's say, hmm, okay, 23 microcoulomb. Let's just make it up. 23 microcoulomb. It holds in the sphere on the surface, and it's empty inside. And you get this charge stored when you have supplied 2 volts. Let's see. Can you find out the capacitance of this by using Q by V? Yes, you can. Yes, you can. Because you know the total charge stored when a certain amount of voltage is applied. So 23 microcoulomb divided by 2. Okay, this works. This capacitance formula is not wrong for spheres. Don't take me wrong. It's not wrong. Okay. The point of that this messy derivation, not messy, pretty clean, I would say. This derivation is you get another formula where less information is required or different information is required. So you just need to know the radius, hence your life is a bit easier. Anyways, I'll move on to this topic. Granted, you don't have any problem with the last one. This one I find pretty neat. What's the time? Uh, 30 minutes. I have this. Oh, this is a brilliant question. Like, literally one of the best questions I've seen, at least from this chapter, if not from the entire syllabus. 9702. You can't do this right now. Once I explain more things, you will be able to do this. 9702 42 MJ22 2022 paper. The entire, you know what? I'll give you a bit of an advice. 2020 till 2022, especially 2021. Really good papers in this year. Okay. Recent papers are also recently good. 24 paper was probably good. I don't know. 23, so. 25 Feb March haven't seen. We'll see later. But these 3 years, 2020, 2021, 2022, good papers, especially 2021. You should check these out. Okay, definitely do these. And obviously the last 2 years, 24 and 5, 4 and 3, and 5 if you have access to the Feb March paper. And if you want the solution, I have quite the explanation over here. Basically, part 3 is the art part. I have quite the explanation over here. I even right now, just looking at it, I don't understand what I've done. I'll have to read this entire thing. But all I remember is this was a brilliant question. So that definitely do. And so capacitors and series in parallel show an energy in capacitors. Capacitor discharge equation. This is a bit long, mostly because I've shown the derivation of this, which is not in your syllabus. This entire log rule and oh, these shenanigans are not in your syllabus. So even if I do teach this, don't worry, it is not in your syllabus. This is this is in your syllabus. Mm, formula. Derivation is not in your syllabus. Derivation, no, not in your syllabus. Okay, quite a bit is not in your syllabus over there, so nothing to be scared of. So I'll start off with series and parallel. Okay, this is definitely in your syllabus. Give me a minute. Okay, so let's look at this setup. Setup on the left, setup on the right. Okay. What is the setup? I have a bunch of, over here I have no resistor involved. Reason being, I want then total EMF to be supplied to the capacitors. Okay. And even if you look at over here, you do have resistor over here, but you will have to work regardless if you have a resistor or not. You will have to, which is why this gets a bit of a complicated question. But yeah, you will have to share the potential between. Okay. So just to make our lives a bit simpler, we're not working with a resistor over here because then the derivation will be a bit complicated. And this derivation is, again, you will have to do it. They may ask you a 3-4 mark question where they will ask you to show how to find total capacitance when capacitors are either in series or in parallel. That is the kind of question that can be asked to you. Okay. Now, what happens when they're in series? I'll show. So I have capacitor. Notice how I'm marking these. C1, C2, C3. C1 has potential difference V1 across, C2 has potential difference V2 across, and so on. And Q1, Q2, and Q3 is basically the amount of charge flowing through them. Let me clarify. These denote charge flowing through. Okay, that is the definition of Q1, Q2, and Q3. So how much charge is passing through these capacitors? Sure, by induction. By induction, that is not a problem. But how much charge is flowing? Okay. Now the question is, the first thing that I do to find the net capacitance of this entire setup. Okay. The first thing that I do to find the net capacitance of this entire setup is compare all the variables. That is, how does charge compare to each other? How does voltage compare to each other? And I'll show it step by step. So first thing I do is I compare the charges. Through this entire circuit that is in series, if over here, let's say 10 electrons are flowing, the same amount of electrons will flow through here, here, and here. Until and unless you're working with a parallel circuit, remember Kirchhoff's law? Until and unless you're working with parallel circuit, electrons or charges do not get distributed. Okay? They don't get divided. Forget about capacitors over here and think of 3 different resistors. What would happen? The number of electrons going in will remain the same and will pass through all of the resistors. Sure, lose energy, no problem there, but the number of electrons remain the same. So charge passing through remain the same. Okay. So if I have Q moving through, Q1, Q2, and Q3 is equal to what? Q. Whatever charge I have moving over here moves through here, 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 and it comes back. Amount of charge doesn't change, regardless of how many capacitors you have in series. Keep that in mind. Okay. So, since same number of electrons travel, same amount of charge is induced at each of these plates. So you may be questioning me right now that how is it that same number of electrons pass through if they can't pass through, they don't pass through, they induce a certain charge. So if 10 electrons are coming in, they have 10 electrons worth of charge, negative charge, and they induce 10 coulomb of positive charge on the other side. And it goes on till here. That is how amount of charge remains constant through the capacitors. So what did we discover? Q is equals to Q1 is equals to Q2 is equal to Q3. Charge has not varied. Good. Has the EMF supplied varied? Yeah, of course. So if you have a certain EMF supplied, right? If you have a certain EMF supplied, it gets distributed between 1 and 2 and 3 capacitors. Okay? So it's equally distributed between these 3 capacitors. So if you sum up the potential difference across here, here, and here, the sum of all the potential difference, PD, PD, and PD, will equal to the EMF, or the supplied potential difference. Get this? So again, I will ask you to think of these as resistors over here. What would have happened? The sum of PD across all of these resistors would equal to the supplied EMF. Clear? Hence, my EMF is equals to V1 plus V2 plus V3. What is V1, V2, V3? I wrote it over here. Good. Now look, can I merge these? Oops, wait a minute. There's no charge. Mm, give me a minute. Okay, so point is, can I merge these two equations? Let's try. Okay, one of the formula that I know of is C is equals to Q by V. And I'll take help of this equation. Okay, so what I will do is I will substitute V. So I say V is equals to Q by C. Can I not make voltage the subject and say voltage is equals to Q by C? Can I not do that? Yes, I can. Yes, I definitely can. Okay, so that is what I established over here. And I input this here, 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 and here. Get the idea? So let's move on to the next step. So for EMF, what is the charge? Well, Q, right? Q. So charge is Q, and what is the capacitance? Whatever the net capacitance is, will be the capacitance over here. Why? I mean, simply speaking, E is equals to E is equals to the total charge divided by, the total charge is equals to total charge divided by the total capacitance. Okay. Why is that the case? Because when multiple capacitors are acting or in series together, they will have a certain amount of net capacitance. Whatever the net capacitance is, I don't know how they act or how they add up together, not my problem. But whatever the net capacitance is at the end of the day, if I divide charge with that, whatever my charge flowing through the circuit is, that should give me the total potential difference or the supplied EMF. Again, if I try to explain that to you, consider all of these 3 capacitors as one big capacitor. In that case, what would I consider? Whatever the potential difference across these 2 points are, is the potential difference across these 2 points. I explained this again, first class and today towards the beginning of the class. If 12V is supplied over here, 12V is also the potential difference across all the capacitors. Okay. Okay. So if that is the case, then whatever the net capacitance is of having three capacitors in series together, I will divide my total current flowing through divided by that net capacitance. And that should give me the EMF supplied or potential difference across all the capacitors. Same as over here. Okay. Same as over here. Granted, we understand that. I have substituted Q, the net current flowing through everywhere in the circuit divided by the resultant capacitance. And this is basically my EMF supply. That is equals to Q1 by C1, which is Q1 basically charge going through one of the capacitor with having potential difference V1. And then Q2 is the charge going through this capacitor with potential difference V2, and so on and so forth. But did I not tell you guys the value of Q1, the value of Q2, and the value of Q3 is equal? I did, right? So what can I say? Since all of these charge values are same, because same number of electrons are flowing through everywhere, I can say ultimately what I have is Q by C resultant is equals to Q by C1 is equals to Q by C2 is equals to Q, sorry, plus, not is equals to, my bad, plus C3. Do we agree with this? So I've substituted Q1, Q2, Q3 as Q. So if I have Q across the board on all numerators, can I not factor Q out and divide it across two sides? Can I not cancel them? Yes, I can. So what will be left with? We're left with this beautiful equation that the 1 by resultant capacitance equals the sum of all inverse capacitance in series. And can you resonate this with this formula? So basically, it is very similar to having resistors in parallel. So net resistance of resistors in parallel is related by this equation. Okay. So it's very similar to that. So when you have capacitors in series, this is how you add the capacitance up. Okay. So if I'll ask you guys a question based off of your intuition. If the capacitor of these capacitors have a capacitance worth 12 microfarad, the total capacitance will be greater than 12 microfarad or less than 12 microfarad when in series. Tell me in the chat or unmute and tell me. Yeah,
Less than
less
12.
than. Exactly. Perfect. So that is how you have this equation working. Very similar to the parallel resistor equation, right? Whatever the resulting will be less than all of these individual capacitance. That is something we have realized when working with the formula again and again and again. Okay. So that is the point. We add all the impulses up. Yeah, good. Okay. So that's the derivation. This derivation is needed. They'll ask you to derive this. Now in parallel, what happens? The opposite happens, to give you a bit of a spoiler. So I have an EMF supplied, charge flows through. Okay. And I have capacitor 1, capacitor 2, capacitor 3. And again, I ask you guys to remember Kirchhoff's law. If Q is going through here and here, does Q get divided or no? Does current get divided? Yes or no? Tell me.
Yes, it does.
Perfect. It does. So the charge will distribute itself in two paths. path 1, path 2. Okay. So the great thing is, if it happens here, it happens here as well. Okay. Again, path 3 and 4. So it has divided itself again. So all of these capacitors have a certain charge passing through them that is different to the total charge. Now, all of these Q1, Q2, and Q3 may be equal if all the capacitance are equal. That is fine. But Q1 is not equal to the total charge, and Q2 is not equal to the total charge, and so is not Q3. Because as charge came through, it got distributed across two paths. Okay, that's the point. So now, when they come back over here, the charges will unite. When charges come back again over here, charges will unite. And the charge over here will be equal to Q. Again, fair? So we understand what Q1, Q2, and Q3 means. Good. Now V1, V2, and V3. Are all of those equal or different? Tell me. And if they're equal,
Equal.
what are they equal to? Yeah. And what are they equal to?
E.
E. Perfect. So the supplied EMF. So whatever EMF I'm supplying, over here and over here, same. Over here and over here, same. Over here and over here, same. So what happens in parallel circuit is whatever EMF you supply, since everything is in parallel, it is the same potential difference across 2 points everywhere in parallel. Which is why all of these capacitors, which are designed in parallel, will feel the same potential difference. And to get it more easier to understand, if there is net positive charge over here, net negative charge over here, causing a net uh, 12 potential difference or 12 volts of potential difference, over here, there's the same net positive charge, same net negative charge, which is why the potential difference across here is also 12 volt. Same over here. Net positive charge, same as the positive side of the cell, and net negative charge, same as the negative side of the cell. So the potential difference across this is also 12 volt. That's what's happening. Okay. So V1, V2, V3 is equals to E, and Q1 plus Q2 plus Q3 is equals to Q. Did you understand that? Let's move on. So Q is equals to the sum of all the currents because they get divided as they proceed through the circuit. Next, what happens to EMF? It is equal to V1, V2, and V3. Same EMF across all the capacitors. So coming to this equation, I'm going to use that equation to find my capacitor net capacitance equation. Can I say Q is equals to C times V? I've basically taken V to the other side or multiplied with V on either side. So I have this equation. Is that fair? That is. So can I substitute this into here, 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 and here? Yes, I can. So let's do that. So my charge over here will be Q resultant times whatever the EMF was is equals to C1, that is capacitance of capacitor 1, times whatever voltage is applied, that is same as E, plus C2, capacitance across capacitor 2, and whatever voltage is applied across that capacitor, that is the voltage E. Same with 3. Now, can I cancel all the E and V's? Because they're equal. Same EMF is applied across all the capacitors, right? So I'll cancel those off, and what I'm left with is C resultant, the sum of all capacitors. Okay? So the capacitors sum up. I mean, capacitances sum up. So this is the math side of it, and you need to understand this. You need to be able to do this on your paper. But I will try and give you a very qualitative response to this as well, or a intuitive way to understand this as well. Think in parallel that all the plates, or let's say this is the negative plate, and this is all the positive plate. So negative, like the charge, comes in, and even though it gets distributed, even though it gets distributed, but the charge demanded increases from over here because there are more plates aligned together. So basically, more charge comes in and gets allocated on each of these plates, because the potential difference of 12 volt, if I'm supplying 12 volt, is applied across all of these capacitors. That is why I'm summing up the capacitance. Because if you had one over here, then it would take the 12 volt and would demand some amount of charge and will store energy. But now, if I have another capacitor in parallel, I have one more plate across which same EMF is being applied. So it will store twice the energy because it has more allocation or more space for charge to be held. Why? Because the same EMF is being applied, 12 volt, 12 volt. So we add up the capacitance. That is an intuitive way to understand without even looking at the formula. Okay. When you have in series, what happens? Whatever EMF is, it is across all of them three. All of them three. Okay. So since the EMF gets distributed between all of these three capacitors, the total amount of charge that you can store becomes less at each of these capacitors. Okay. So your net capacitance of even having three capacitors in series decrease. Okay. So on one side, I'm adding up the capacitance. On the other side, I am adding the inverse of the capacitance to find the inverse of resultant capacitance. There. So those are the two things, two ways that capacitors can be set up. Okay. And this great uh, example, try that. And the last thing I'll do is find the stored energy. Okay, this is what I'm going to end it with. And the last thing that you guys will have is discharge, which is relatively small, but I've made it long. But I'll show it to you. No worries. Now, this stored energy bit, which we would end off today's class with, you and I know that energy is stored in a capacitor. Great. We both know that. But how do I find it out? How do I find out how much energy is stored? Now, usually, some of my students, when I ask this question, what they said, which is very fair, and it's great that they even answer this, is voltage is um, work done per unit charge. So, how do I find out total energy stored in a capacitor? I will find the total voltage across the capacitor, right? Multiply it with amount of charge stored on one side of the plate, Q, and that will give me total work done. Okay. Now, do some of us agree with this formula? Yes or no? Do you think this is accurate? Yes or no? Yeah. So technically makes sense because whatever the net voltage is multiplied with the total amount of charge that has been stored, and that should give you the total work done. Only the issue is initially the voltage and charge is not the same as the final stage. What did I just say? Remember over here how the charge accumulated varies with time and how the voltage accumulated varies with time. Over here, initially, for one thing, if I'm, let's say, storing 100 coulombs of charge, the first 1 coulomb of charge, when going to the capacitor's plate, is not feeling, let's say, 12 volt, but feeling, let's say, 0.1 volt potential difference. And then when the next coulomb of charge goes, it feels, let's say, 2 volt of potential difference. So more work is done on that 1 coulomb. Next, when the next 1 coulomb goes, it feels 3 volt of potential difference. Now, what happens? It does more work done on the next 1 coulomb of charge. So, do you see what's happening? On all the charges, on all the charge that has been accumulated, different amount of work was done. If I have stored 10 coulomb of charge on one side of the capacitor's plate, all of these 10 coulomb of charge did not have 12 volt worth of work done on them. They had different amounts leading up to the last 1 coulomb having 12 volt of work done. So would you say you still think Q times V would give you the true value of energy stored? Yes or no? Do you think Q times V would give you the true result of the energy stored? Yes or no?
No.
No. Okay. But it's not entirely invalid. If from the get-go the potential difference supplied was 12 volt, then what you're saying is perfect. So if I have uncharged plates over here and my electrons start flowing, right? And the potential difference somehow, I don't know how, is over here worth 12 volt from the get-go, then yes, any charge flowing here will feel 12 volt worth of work done on them. That's fine. But it is just that initially the potential difference across over here is not 12 volt. It's 0, then 1, then 2, then 3, then 4, then 5, and then finally 12 volt when the charge is complete. Charging of the capacitor is complete. So it happens in stages, it happens eventually. It is not um, immediate, is what I'm getting at. So all of the charges will not have same amount of work done on them. And I'll show this to you. Give me a moment. Okay. So basically, how does energy get stored? Okay. So initially, when you have a few electrons going in, right? Few electrons going in, the amount of potential difference is very little. So the work done on them to go from this plate, this side to another side is less. Okay. So if I try to paint a picture for you guys, where do I have a diagram? Do I have a diagram? Okay. So I can explain two ways. One is this, which you can read out. But the other way, I can go back to the previous diagram. Okay. So the first electron that goes, what happens? It easily goes to over here because over here it is neutral. Okay. I'm just giving you an intuitive picture. I'm just describing it. I'm not showing you the formula or anything. But the first electron that goes from this cell over here, it is neutral, doesn't feel any repulsion. So the work done Pretty much zero. Next electron goes, since there's already an electron, feels a repulsion, I do some amount of work done. Let's say 1 joule worth of work done on one electron, so 1 volt. As the next electron goes, I do, well, 2 joule of work done on this. Because there are already two electrons there. I'm facing repulsion. Okay. And now I have done 2 joule of work done on this one electron. So the buildup of over here is 2 volt. Third electron goes. 3 electrons already there. I'm getting repulsion. So I have done more work done on this electron. How much? Let's say 3 joule. So over here, what the energy stored is 3 joule per electron, so 3 volt. Am I being able to paint a picture in your brain? Right? So you get the idea. As electrons keep proceeding, different amount of work is being done on each electron. As more electrons go, more work is being done. So if I try to show that to you, it looks something like this. Uh, something like this. As the amount of voltage keeps increasing at the capacitor, the amount of, sorry, as the amount of charges, I mean, you can explain either way, but as the amount of charge increases on the plates of the capacitor, the amount of work done on each electron increases as well. What does voltage mean? Work done on one electron. So as more electrons get stored up, more work is done on each electron. So it's a proportional line. It's a straight line. Fair? So what is the total work done? The area under the curve. You are right to say that it is Q times V. You're absolutely right to say that. But this is not the real equation, in the sense, if you take the total charge times the total supplied voltage, let's say 10 microcoulomb or 10 coulomb, let's say, and 12 volt worth of energy, sorry, work, potential difference supplied, and you say total work done is 120 joules. Nope. Nope. It is Q times V, but the area under this curve. So initially, if one coulomb of charge goes, and I'm doing 1 volt of work, 1 times 1 plus 2 times, let's say, 2 volt of work, 2 times 2, 4, 1 plus 4, then plus 9, let's say, then I don't know, so on and so forth. Okay. So it keeps adding, you're adding each of these points together and you're getting this triangle. So area under the curve over here gives you the total work done. And what is that area under the curve? How can we classify this? Notice this can be classified as a square, or it could also be a rectangle, doesn't really matter. Could be a rectangle as well, like this. And if this was the curve and this was the shaded region, then it would still be half times Q times V. How so? So half times total charge stored and the potential difference applied. Okay. Okay. Fair. So if this is the total, this position denotes PD applied to the capacitor. Okay. And this denotes total amount of charge stored. So for that total amount of charge stored, for certain PD being applied or potential difference being applied, how do we find the total work done in the entire process, or the total amount of energy stored? It is half times Q times V. Makes sense? Do we understand this? Yes. Are we good on this?
Yes.
Okay. So anyone asks you to find the total work done in charging up the capacitor, or how much energy is being stored, this is how you find it. Okay. So energy stored half times Q times V. I can further find a different formula for this. So I can say Q is equals to CV and substitute it over here. And what I get is half times CV squared. This is another formula. This is simple substitution, nothing else. I'm just substituting it. I can do something further. I can substitute V is equals to QC over here. So half times C times Q by C whole square. What I will end up is half uh, C Q square. So half Q square by C. This. These are the three formulas of energy. No one, the rest will come automatically to you if you know how to substitute expressions. Okay, these are the three equations of energy. And with that, we're done with today's class. Okay, any question for today? Anything else? We have covered a lot today, decent bit. One last thing left, capacitor discharge equation, which I will show it to you. First, I will need to decide do I want to show everything. There's integration. Uh, I mean, you can do it if you've done pure math. You can do it, but I don't know. I would want to teach the entire bit. It'll take me 30 minutes, 20 minutes, 30 minutes, and explain it. But yeah, that's it. Any other question? We're done for today's class. All good? Okay. 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 Perfect. Then we'll end the class for today. You all are welcome to leave. Thank you for attending. See you guys next class. Next class will be Sunday. Yeah.
Wait, do we have the link to this class?
Yeah. Okay. Give me a moment. I'll attach it right now. This today is 18th. Yeah, it will be automatically uploaded over here. Just show up. Yeah, day 15. Okay, all good.
Okay, thank you, sir.
Okay, thank you everyone. See you guys next class. Bye bye.